CTOD is also a criteria, and there is also a standard for defining fracture toughness based on CTOD. But that was your assignment, to find out how much crack opening will happen for certain value of stress intensity factor. Okay, so now today we will start with another parameter, which is for fracture toughness, it is going to be the last parameter. So the problem with K was that you have a plastic zone, and in this plastic zone K is not valid. Okay, and we tried all the possible things to avoid our measurements so that it doesn't fall in plastic domain when we use equations and theoretical calculation. And for experimental measurements, we ensured that the plastic zone is very small so that the effects can be ignored. And because of that, we got a criteria that our thickness should be greater than 25 times of this plastic zone. Scales with plastic zone radius. So plastic zone radius should be very small. So suppose that I have a steel for which my sigma naught is 200 megapascal and K1C is 100 ampere root meter. This is a fair assumption to make because we do have materials, a lot of them, which has yield strength in this range and K1C in that range. So can you calculate how much thickness of this specimen you need to have? How much?
So 6.25.
Approximately 6.
6.25. So this is 0.5, right? So this is 25 into 0.25, which is 6.25, and 6.25 meter. Or right? So ampere root meter. So root meter square is meter. 6.25 meter is how big? 1 meter is how much in feet? 3 feet. 3 feet. So 6 meter will be 18 feet. 18 feet. So the tallest person,
6 feet.
Imagine 3 times of that, and you have to make a specimen which is that thick. Okay, and the W will be double of that, right? So 36 feet, and then the height will be 1.25, 1.2 of W. Okay, so how much? 41, 42 feet.
बिल्डिंग से ऊपर चला
बना तो लिया सैंपल किसी तरह, अब उसके लिए यूटीएम कहाँ से आएगा? So, is it 25 or 2.5?
So 2.5.
2.5.
Because that is completely unrealistic.
0.625.
So this is 0.625 meters. And how much is 0.625 meters? 625 millimeters. So 62.5 centimeter. right?
Still long.
So 62.5 centimeter is how much? Approximately 2 feet.
Yes.
Okay. So then you have a value of 4 feet,
Still.
5 feet. So फिर हाइट के आसपास का सैंपल खड़ा करना पड़ेगा. कर दिया. फिर से यूटीएम नहीं मिलेगा उसका. बिल्डिंग जितना बड़ा तो सैंपल बहुत बड़ा होगा. That was the calculation mistake. Okay. So one problem is that you have to have the idea of K1C in order to measure K1C. And second problem is that for all the materials you will not get enough thickness so that you can do this test. So what can we do? क्या करें इसका? So the standard is asking us to make brittle materials so that our testing becomes easier. We can follow the standard. Okay? So if we follow this, we cannot develop materials. Right? If we develop ductile material, then we cannot test it. So what do we do then? So the problem is coming because of plastic zone. Okay? And if you remember, this field started with Griffith. He tested on glass. Then Irwin was working with brittle steels, BCC alloys, which were breaking when the ship is just on the port, and so you need to revise your theory. And then time spent, although Irwin was working on high velocity impacts also, so dynamic hitting of something on the target. So so then we need to deal with plasticity. We can't ignore the problem. So everyone does it. No? So if you have a problem, then you try to avoid it. If you have an assignment, you try to avoid it. Right? If you have an exam, you try to avoid it. अब तो ऑनलाइन एग्जाम तो बैन करना पड़ेगा. चैट जीपीटी के आने के बाद उसको बैन करना पड़ेगा. Because now you have answer to everything. Okay. I don't know. If you have not tried ChatGPT, you should. It's a very good thing. I tried it.
Yes.
And I was not telling my PhD students, but now I have disclosed this information.
Thesis भी लिख देगा वो.
नहीं, thesis नहीं. Code लिख देता है, yes.
Coding करना.
So if you ask it to write damage code for hydrogen embrittlement, it will write it. So you can also try to ask this platform to write it for your specific material, and it will write it. But you need to check it, okay, because it will not give you citations. So you need to check where this code the AI has taken, and if you do blindly, then you are going to fail miserably. Okay, fine. So maybe in next 10 years we will have good AI, so we'll not need PhD students. We can just ask the softwares to do some research. But you see what will happen with this AI. You think the books will be vanished? Books and research articles, there will be no need of it? No? Yes, there will be. Because this AI is taking information from the books and articles. It is not creating information. किसी को तो लिखना पड़ेगा. ठीक है? तो अब suppose, so now you stop doing research and you start using this platform. So then you are writing your thesis with the existing articles. Okay? So there will be a saturation point. उसके बाद नया information रहेगा ही नहीं. खत्म. Everyone will have same thesis. Okay? But it's a good thing. You can try using it in a good way, not misuse. Don't misuse it. Okay. So dislocations also try to avoid any obstacle, and when it cannot, then it has to do something about it. Okay. So we have seen that now we cannot avoid plastic zone. So we have to go inside the plastic zone now. We have to deal with plasticity. We have to deal with the conditions where the whole specimen, so if you keep on increasing stress, then this plastic zone will increase, and then you will have a plastic zone like this. So this whole area inside the two lines will be plastically deforming. It will not be that everywhere you have plasticity. That will not happen, because it acts like a hinge then. Okay, so you have tension here and then you have compression on the back side. So you will have a point where there will be a nullifying effect of tension and compression. Okay, but if you load it a lot, then of course this will also join and you will have complete plasticity everywhere, and then you will not be able to make out that which zone. So before this stage you will have something like this, and here we'll have back face plasticity. Okay, so the area at the back side is also deforming plastically, but there the strains are compressive. Okay, and when crack moves, it moves. So when crack is here and when crack is here, the plastic zone has moved, and you will have a plastic wake. So an area which is already deformed plastically has opened up, but it is deformed plastically. But this will not move, because it cannot move. It will grow, but it will not move. Okay. And what will happen if we have strain hardening material? So the material we usually have in metallic conditions. So we don't have ideal plasticity, we have strain hardening. So what do you think, for strain hardening material, the plastic zone size will increase or decrease?
Decrease.
It will decrease. Yes. With increment in yeah, it will decrease. So you can calculate again K1C by sigma naught. So K, whatever K you are applying, that is increasing, that is applied load, right? And sigma naught is also increasing, because now you have strain hardening. So the plastic zone is going to decrease with the strain hardening, or strain hardening material. Okay. Okay. And here we have a lot of things going on at the crack tip. So this area is plastically deforming, but there is an area whose shape I do not know. You can calculate that. Was there an assignment to calculate plastic zone also? No? You should do it. I showed a code in the class, no? Where you can write the formula for plastic zone, and then there was a red curve and then there was a blue curve. One was for plane stress, one was for plane strain. Okay, so you should try coding that also. Yeah, to calculate plastic zone. Okay, that will be your last assignment before mid-sem. Okay, so there is a zone where what will be happening now? So at crack tip, what is happening? So there is a reason where plastic deformation is happening. So you see, if you proceed along this path, then you have stresses increasing, okay? And then you reach here and you hit sigma naught, okay? For theta is equal to 0, you will be hitting sigma naught here, okay? Now you are in plastic zone, so the equations are different. And then you keep on, so as you proceed, you are also proceeding on this path, right? Initially you are elastically deforming, and then you hit sigma naught. So this is the point, and this is the point. Both of them are same for a material point, right? And then you move ahead. So you are again moving ahead on this curve. So there will be a point where you have crossed UTS. Then what will happen?
Necking.
नेकिंग कैसे, ये क्या टेंसाइल डिस्प्लेसमेंट थोड़ी है, क्या होगा, टूट जाएगा, इसके बाद फ्रैक्चर ऐसी है, यहाँ पे तो फ्रैक्चर नहीं है, it will go like that and then it will fail. So what will happen? Stress will decrease. Hmm?
No, continuously increasing.
Continuously increase till eternity. What will happen? Plasticity के बाद का phenomenon क्या है?
So ये
Damage होगा. Okay? So you will have a zone where you will have void formation. Okay? So now if you do a sectioning and look at it under scanning electron microscope, then you should see a lot of roughness. It will not be flat as it looks. So somewhere close to the crack tip you will start seeing voids, and then you will see bigger voids and smaller voids. Then you will see even bigger voids and coalesced voids and smaller voids and some voids. Okay, so you are progressing in damage also. So in this region where you have a lot of damage, plasticity is also not holding, and then there is a zone where we don't really know what is happening. Okay, so that's like a, I don't know, some people don't like this analogy, but still I want to give this analogy, is that it is like a black hole. So in black hole you have a boundary which is called event horizon, right? So event horizon, all the equations of gravity and theory of relativity works, but beyond that you don't know what is happening. Okay, so similarly you have a zone where you don't know what is happening, and for the sake of convenience we call it process zone. I don't know what is being processed there, but it is called process zone. Okay, so a guy comes from a background of mechanical engineering and good in mathematics. Okay, and he applies the concept of that he takes something out, a small piece at the crack tip out, and when you take it out you have some traction on it. Okay, traction is a vector which is simply the dot product of the tensor and the normal vector. Okay, and then he calculates that how much is the stored energy and how much is the applied energy. How much energy is applied on this line, along this line, and how much energy is stored in the form of elastic energy. Okay, and in order to apply this concept of line integral, which is applied in physics, so Rudraksh will be knowing. Okay, so if you have to calculate work along a path, then what do?
F dot dr.
F dot dr. Well, you also know. Okay, so along a line, you can calculate F dot dr,
Yes, sir.
and this defines the work. Okay, and if you take a closed contour, this will be 0. But this is for a special case where work acts as a potential. So the condition here is that F must be a conservative vector. And for this to happen, F must be a gradient of a scalar, some scalar. Okay, so that scalar can be potential energy. So it must act as a potential, and if you have a gradient of a potential, then that acts as a conservative field, and then a line integral becomes path independent. So you take any path, and when you calculate the line integral, meaning whatever is the function which you have written after integration, those are calculated on the line. Okay, and it follows a direction. So you can go on a line in two ways. Okay, so whatever value you get for this will be positive or negative depending upon in which direction you are going. So if you go counterclockwise, then you get a positive value, and if you go opposite, then you get a negative value. But the advantage of this is that I take this path or this path or any other path, it's going to give you the same value.
Yes, sir.
Okay? So,
Sir, but plastic deformation is not conservative.
why not? If you can define a plastic potential, well, yes, you are right. Plastic deformation is not conservative. That is correct. So we can't do that. So probably James Rice is also thinking about the same thing. And you probably have his soul in you. I don't know why I'm talking like a tantric. so James Rice is also thinking that this is a good idea. Maybe he's reading about line integral in his holiday. And he's also thinking, इसको लगा सकते हैं क्या plasticity में? Huh? So then what he does? He does the same thing which all physicists do. Okay?
Assumption or something?
Yes. Yes. So physicists and mathematicians, they are very good in doing something. Is that assuming things and then making tan theta is equal to theta. Okay? And ignoring higher order terms. These are the three things which all of us do. Okay? So he assumes.
इसी assumption की वजह से तो ये था ना कि यहाँ भी एक assumption थी कि plastic deformation हमारा कम है इसीलिए हम J पर
Assumption नहीं है, वो तो ensure करना पड़ेगा. That you must ensure. There is no assumption there. So plastic zone, you have to keep it so small that the error becomes smaller. There will be an error because of plastic zone, and there will always be a plastic zone. अगर वो plastic zone इतना छोटा है that I can act like a physicist and I can ignore it, then I am good to go. Okay, so it's not that they are assuming that there is no plastic zone. Otherwise, there will be no calculation of RP. Okay, so so now Rice is thinking what to do about it. So what does he do? He assumes. What does he assume? That it's an elastic material. Okay, an elastic material which is deforming plastically. How can that happen? So he assumes that this is stress strain curve. So what will be the difference if I have to call it an elastic material? If I want to call this material elastic, not elastic plastic. So
all the strain should recover.
yes, तुमको grade अच्छा मिलना चाहिए. Okay, so the difference appears only when you unload. If you keep on loading, then there is no difference between an elastic material and an elastic plastic material. Okay, if you unload an elastic plastic material, then it will follow this path, and you will have some amount of strain which is recovered and remaining is not. And if it follows the same path, then it is an elastic material. So Rice says that I will not unload. I will never unload my sample. And if I don't unload, then it is an elastic material. Okay, so then it becomes a nonlinear elastic material. So he can define a normalized form of strain is equal to sigma by sigma naught plus some constant into sigma by sigma naught to the power n, and this equation defines the whole stress strain curve. Okay, Rambach-Osgood equation. And when you relate stresses with strains in these kind of formulations, these are called constitutive relationships. Okay, so the speciality of this equation is that for each value of strain you have one value of stress and vice versa. So it will always remain on this path. Whether you increase the stress or decrease the stress, it is going to give you one value, right? And the difference for an elastic plastic material will be when you unload, for the same value of stress you will have different values of strains, right? That is not appearing in this equation. If I unload, then also for the same amount of unloading, I will come back to this path and I will get this much strain only using that equation. Okay, so that equation is defining a non-linear elastic material. The constitutive relation for that. This is called deformation plasticity. Just a name. Okay. So now your problem is solved. Okay.
तो ये तो पिछले से फिर से कंट्राडिक्ट हो गया ना, आप कह
कैसे?
रहे हो कि अनलोड नहीं करना और एक
पिछले में अनलोड करने से तो मना नहीं किया था।
इसमें इसमें सर पर आपने जो मटेरियल की 3 शेप्स बताई थी, एक तो लीनियरली जा रही थी और एक में आपने बताया था कि मैक्सिमम पे जाके जब एकदम से ग्रोथ होगी तो वो डीलोड होगी, उसमें अनलोडिंग होगी। तो मटेरियल में अनलोडिंग तो होगी।
यू आर टॉकिंग अबाउट दिस बिहेवियर
सर सीही वर्सेस
जो मैक्सिमम जाके नीचे आ जाता था ना, जैसे एक
यही मैक्सिमम है ना। आर यू टॉकिंग अबाउट दिस स्ट्रेस स्ट्रेन कर्व?
सो जब क्रैक पे हमारी ग्रोथ होगी,
हाँ,
तो उसमें जब एरिया कम होगा तो उसमें जो लोड है वो कम होगा ना, स्ट्रेस कम होगी उसमें।
नहीं, स्ट्रेस क्यों कम होगा?
एरिया घटेगा तो स्ट्रेस बढ़ेगा।
स्ट्रेस कम
नहीं,
बढ़ेगा।
अनलोडिंग का कहा था ना, उसमें जो आपका था डिफॉर्मेशन कांस्टेंट रख रहे थे जिसमें
क्या,
और जिसमें हम वो कर रहे थे
डिस्प्लेसमेंट
कर रहे थे, डिस्प्लेसमेंट कांस्टेंट रख
yeah, we will discuss about those. We will discuss about those things. So I don't know what are you talking about, but there are 2 cases, and probably those 2 cases will explain whatever confusion you have. So one is that this is engineering stress strain curve, okay, and that goes down. But if you plot true stress strain curve, that will never go down. It will keep on increasing, and then there will be fracture. Okay. So assume a small box in which you have nothing. It's a representative volume of your material. It's a very small volume, and then you apply stress on it. Okay. So it elastically deforms, and then it deforms plastically, and then there is damage. Okay. So you have voids in it, and then you cut along a section. Okay. So initially, when there was no deformation, you had an area A. Let us call it A0. When you have voids and then you cut it, then you have a different area which is smaller than A0, isn't it? Because there are voids now. Okay, it has become porous. So the area has decreased, so the stress will be increasing. Okay, so that is what is happening here. Damage is appearing also after necking macroscopically and both microscopically. In both cases, you have reduction in area, reduction in load bearing capacity. The another thing which you are talking probably is that when crack opens up, then you had some material points which were connected, and when crack opens up, these material points are now stress free. So there is an unloading. Okay, wherever these stress points were, so this point probably was here, the crack has opened up and this has now gone to this value. So unloading has happened. Okay, so if it is elastic, it will go there. If it is plastic, it will go here. Okay, this is an unloading. This is a true unloading. But Rice does another thing to stop this thing. Okay, he is saying that my crack will never propagate.
Static.
Okay, I am just opening it to the extent that it, so just before it starts propagating. Okay, so now both of the problems which you said, I am pretty sure the soul of Rice is there in you. So both the problems are now gone, right? So it's a non-linear elastic material and the crack is not opening up, so there is no unloading, and you have to remember these assumptions. Okay, so in that case it will act as a conservative field and I can define a line integral. Okay, and so I define a line integral along any contour, and the energy which is absorbed in it, I can write it as strain energy density into the area, because volume he is considering in 2 dimensions, so area into whatever unit of the thickness is, that is your volume. Okay, is it okay? So, and then you subtract the amount of energy which is supplied, which is applied. Okay, so you have a traction, and then because of that traction you will have a displacement gradient, and that you have to count on small pieces of this contour. So if you have a contour like this, then a small piece on this is ds, and on every ds you will have different normal vectors. Okay, so sigma dot n will give you traction, and then at every point you will have different values of displacement vector. So you'll have del u by del x, and then you have to calculate this line integral. If you calculate this, then what are you calculating? You are calculating how much energy is either stored or eaten by the material, right? So जितना पैसा दिया उतना खर्चा हो गया, तो कुछ बचा नहीं, net result will be 0. Okay, and then you know that if you give some money and then you earn some money out of it, which rarely happens, that depends how much money you are giving. If you give me a lot of money, then I will earn more than that, but reverse can also happen. Okay, so for a closed contour in a continuum space, there is no possibility of creating any energy, right? A material cannot create energy unless you have uranium in it. Okay, or uranium will also, so we are not counting those energies. We are not counting electrical, magnetic, radioactive energies. We are in mechanical space, we are in continuum space. Okay, so if I happen to have a Martin-Zittig transformation which will cause volumetric expansion when the stress increases, that will cause residual stresses, so that might cause some deformation. And also Martin-Zittig transformation will cause plastic deformation in the material. Okay, it will cause twinning in the material. So there you might have some energy which is created, but really I don't think so, because that is happening because the stress is increasing. So you are supplying some energy, only then Martin-Zittig transformation is happening. If you give temperature, then you are supplying thermal energy. Okay, so there is no possibility in a continuum space that energy can be created. Can it be absorbed? Can something take away the energy? So if you have a hole inside it, if you take a closed loop and you have a hole inside it, so path independent means that the value of this integration depends on the starting and ending point. That is why it is path independent. Okay, and if the starting and ending points are same, it is going to give you 0 value, right? So for a closed contour, it is, this line integral is going to give you 0 value always, unless you have something inside it. Okay, if it is a continuum space, then it is okay. But if it is a not continuum space, if you have a grain boundary, which you have, but we don't go to that scale. Okay, but if you have, let us say, 2 different materials, one has an elastic deformation different from another one, then in that case this will not be 0. Okay, so you have an interface which is acting as a source of energy. If you create a hole, that acts as a source of energy. If you have a crack, that acts as a source of energy. Okay? So whatever is the source of energy, that is going to give you some amount of energy. So this line integral is going to be equal to that value, unless that source of energy changes its behavior. It starts producing more energy or less energy. Okay? So assume that if the crack is not growing, it is going to not change its property of changes in the energy, whatever is happening. Okay? So that will be defining, so this line integral, if you calculate along a contour which encompasses a crack tip, then that is going to give you a particular finite value. Okay? And that finite value is going to define the crack in a unique way, क्योंकि वो crack की ही वजह से आ रहा है, कोई और चीज है ही नहीं, कोई और चीज नहीं है, होती crack भी नहीं होता तो zero होता, zero नहीं है, इसका मतलब कुछ है, वो क्या है, we know, it's a crack. Okay, and there is a material which is deforming in a different way, which we don't know about, and that is happening at the crack tip. So with the crack tip there is a process zone. Both of them are acting as a source of energy or sink of energy. Sink of energy if the value is negative. Okay. So Rice does this and says that by using this line integral and assuming the material to be non-linear elastic, we can define something, and he names it J. Why? Because his name is James Rice. Okay, and this is equal to the rate of change of energy per unit crack length. So energy release rate, which was also defined by Griffith, right? So G was also this. Now crack is not opening, so how can that happen? So you can take this contour for two different crack lengths, and in these two different crack lengths you will have different values of J integral, because crack tip is not same, it's different. Okay, it is dependent on how much crack depth is there, right? So, and we know that stress intensity factor is going to change because of the crack depth, and constraint is going to change because of crack depth. So stress and strain conditions are going to be different on the crack. Because of that, you will have a different value of J integral for two differently deforming cracks. Okay, so with the same thing what we did for Griffith, where we drew two straight lines for different values of crack length. In this case, we will be drawing not straight lines, but a curved line, because now we are assuming the material to be non-linear elastic. So it is basically very same to what Griffith is doing. Griffith has also applied thermodynamics, energy balance. Rice is also applying the same thing using a mathematical concept. Okay, and then assuming it to be non-linear. So it really becomes Griffith theory. Okay, and this curve will be for a crack length which is smaller than the crack length for this curve, because for a bigger crack it will absorb less energy, it is going to go to a lesser value of force. Okay, so for this and this becomes a case of constant displacement. You can also do the same thing for constant force, and for that case it will be something like this. Okay, so this becomes, so dP is equal to 0, right? And how can we calculate the value of energy which has been released when the crack has grown from A1 to A2? How can we calculate how much energy is released when a crack has grown from A1 to A2? By finding the area under the curve, isn't it? So you tell me then what will be the value? So you will have two different values for load controlled and displacement controlled. Okay. So let us take displacement control and then tell me what will be this area. So the upper area will be what? क्या होगा वो?
half b into delta. half b into delta.
Triangle थोड़ी है.
मतलब इलास्टिक होता है.
ओ इंटीग्रेशन से निकालना.
तो बोलो इंटीग्रेशन of p
p delta.
p d delta.
d delta.
Okay, and this will go from 0 to delta.
Yes sir.
Then what will be the value for lower curve? Also same. Isn't it? So the force will be a function.
Yes sir.
P will be different. Okay. So we can define del u du. We can define like this, no? Because you will have different forces for different values, right? So what will be du by dA? You will simply have 1 by dA or 1 by delta A into integration P d delta, and this is for constant force. Okay? And the opposite case will be when you have force constant. Then in that case, you will have what? Du by dA is equal to 1 by delta A integration of 0 to delta into dP.
Yes sir.
But this will be negative.
सर कांस्टेंट फोर्स के लिए जिस एक्सिस पे p उस पे इंटीग्रेट नहीं करेंगे.
उसी पे करेंगे तो नेगेटिव करना पड़ेगा इसको. Yes, that is what. So this means that only. Delta dP means you are integrating on this axis, and negative of that will be that. Okay. So this. So that is called complementary energy. Okay. So we have shown for Griffith that for load control and force, so displacement control and force control, in both cases this comes us to be same, that we have derived. In this case also, if you derive and there is a complicated derivation, then both of the things comes out to be the same. Okay. So this formulation can be used for finding out the J integral experimentally. The equation, the line integral equation cannot be used for measuring the integral, because you will be doing a test, and how will you measure the stresses and strains at different on a line integral? How will you do it? Right? So you need another formulation, which is this one, to use it for the measurement doing an experiment, similar to Griffith. Okay? And this, because this theory is good in plasticity, when we assume it to be non-linear elastic, then it is valid inside the plastic zone also. Okay? Because we are following both. So we have one equation for stress strain, and that is valid inside plastic zone also. Okay? So now if you conduct experiment, you don't need to fulfill this criteria. And because J is equivalent to Griffith, this becomes equal to K square by E prime. Okay? And stresses at the crack tip can be described using this J integral value with this function. This you don't have to write, these are there in the books. Okay? And strain, you can also calculate, you will have similar thing, and you will have n by 1 plus n, and this basically is coming from Osgood-Ramberg equation. Okay? This is coming from this. Plus, you have alpha. From this it is coming. Okay? So, if I have root r singularity, then what will be the value of n? So, stresses are varying with r to the power minus 1 by 1 plus n. Right? So, in order to have root r, 1 plus n should be equal to 2, so n is equal to 1, that is ideal plasticity. Right? For strain hardening material, this will show a different singularity. Okay? So this also will become infinite at some point. Right? Or not? This can also become infinite. When will it be infinite? When r goes to 0, what happens? When r goes to 0, this is infinite.
Yes.
It is the same thing. It is the same thing like Irwin's K formulation. Right? But K could not go inside plastic region. This can go inside plastic region. So the R can be very small, but it cannot be, still cannot be 0. Okay? It still cannot reach 0. So this is also defining a singularity. You have singular, so you have asymptotic curve again for a very small value of R. But we did not have this kind of representation of stress strain in case of George Irwin, right? Because that was only valid for elastic theory. This is coming from Ramberg-Osgood representation of elastic plastic stress strain curve. Okay, so this was done by नाम बताओ तीनों का, यही आएगा एग्जाम में. Hemant, Rahul and Robin. Okay, Rahul भी है. नाम तो सुना ही होगा. So this is called Hutchinson, Rice and Rosengren singularity. Okay. And this can define stress strain in the plastic zone. Okay, so inside the plastic zone, if you want to find out what is the value of stress here and strain there, you can use this formula and you can calculate it. But very close to the crack tip, you shouldn't do it. And in order to calculate those things, you need the value of J, you need the value of IN. IN is an integration which is a function of N. What is N? N is that. Okay, N is strain hardening exponent for Ramberg-Osgood equation. Okay, so the values of O, you also have functions of theta here. Okay, because it will also be a function of theta. And those are not stress strain, they are just symbolized. So they are dimensionless functions. That's why I have a cap over them. Okay, and those are different functions for stress. So that's why I have represented with sigma with a weird curved hat on the top. Okay. So I think this is okay to initiate J integral, and then we'll explain from this in the next class.